Okay. Yeah. Good morning, everyone. Distinguished guests, participants. Let me first start by expressing my sincere gratitude to the organizers for inviting me to this very important event, I think, because sustainable energy is something the world has a big need of, because there are still people who ignore that there is something like climate change and global warming, actually. So I think these kinds of conferences are of immense importance to counterbalance that. Okay, today I'm going to talk about LED lighting, which actually has taken the artificial lighting industry by storm over the past 15 years or so. So I'm going to talk why that is actually, and also that LED lighting is at the moment the greenest form of artificial lighting. Now the thing is, like, LED lights can also be used as a source of wireless communication. So a concept that is known as visible light communication. So I will also talk a little bit about that and the applications of that. So I will start my talk with semiconductor and diode basics, because LED is a semiconductor and the D stands for diode. Now, don't be afraid. The only background you need is basic high school physics and high school chemistry. So I will limit myself to that, but at least that you have an appreciation by how is light produced by LEDs. Then I will talk about LED lighting, high brightness LEDs, then the drivers that are used for LED, and then what is the LED advantage. And we will see that there are only advantages of LED lighting compared to traditional artificial lighting, something that rarely happens in technology, that something new only has advantages. Usually it comes with disadvantages as well. For LED lighting, it's not, it only comes with advantages. Then I will talk a bit about eye safety issues. There is a lot of controversy around. Some people say that LED lighting is dangerous because it emits blue light. I will counter that actually in a recent study of the European Union, that there is actually no reason for concern. Then I'll talk about the VLC concept, which VLC is a type of optical wireless communication. So I will briefly introduce you to the other forms of wireless optical communication and the various applications. Then what are the VLC antennas? And then the merits of VLC. And with VLC, there are also drawbacks. So I will also mention the drawbacks of VLC and how to overcome these, or at least to a certain extent to overcome these. And I will conclude my presentation with a brief overview of the optical wireless standards that there are. So I'm going to talk a little bit about the semiconductor basics. A semiconductor is a material with a conductivity between that of a metal and an insulator. So it consists either of a single element that has 4 electrons on the outer shell, or a compound of elements that have 3 electrons on the outer shell and 5 electrons on the outer shell. So on my next slide, I mean, the most well-known semiconductor is silicon. Now, silicon, as you can see on this slide, has 4 electrons on the outer shell. Now, instead of having that big atom structure, we're going to simplify that by a nucleus connected to 4 bars. Those bars symbolize the electrons on the outer shell. Now, with 4 electrons, it's easy to find a structure where you get 8 electrons on the outer shell. Everyone knows that a stable component in chemistry needs to have 8 electrons on the outer shell. So, so it has a crystalline structure as well. And actually in that state, it does not conduct electricity. Now what we will do is, and you see that on the second structure, which is a P material. So we're gonna put a material in it with only 3 electrons on the outer shell. So which you see there in red. So there is actually one place available to attract an electron. Then secondly, there's something that we call P material, where actually we're gonna put some electrons that have a 5th electron on the outer shell. And at room temperature, that is actually that comes loose from the electron bound. So that has a few free electrons. Now, a diode and an LED and a photodiode are actually essentially the same. So a diode structure is a semiconductor device that consists of, on one side, a P material and an N material. They're not glued together. In practice, they are grown on a substrate, actually, but I'm not going into the details of that. So now what happens actually is that, do I have it? Okay. What you see here, if I put them together, then actually the holes that you have in the P material are going to attract electrons in the N material. So you create an intrinsic zone between them, but it's not going to migrate indefinitely, because actually the N material becomes positively charged, the N material becomes negatively charged. So you have a voltage over that, and that voltage will prevent indefinite migration, actually. So now how is light produced? As I just told you, if you put an P and an N material together, there is a migration from electrons to holes, and when they recombine, it actually releases a packet that is known as a photon, which is the elementary packet of light. Now I like to point out the energy of such a photon is proportional to the frequency. So the higher the frequency, the more energy it is. Now in light, the higher frequencies are blue light and UV light. So that's also why I come back to that later on eye safety issues. The blue light is the light with the highest energy. Now, okay, now we're going to put a forward voltage over a diode. What you get then is that there a current flows. As we know, the conventional current is opposite to the electronic current. The reason is traditionally, before it was known that electrons moved from negative to positive, people thought they would flow from positive to negative. So that's why we still have that opposite current. So what happens then is you're going to move electrons to fill holes. Again, they recombine and they produce light. So that's actually how light is generated in LEDs. Now, the thing is, a photodiode does the opposite thing. The structure is different, but the principle is the same. It works opposite. If light falls in, it's going to release an electron hole pair. So it's going to move that. The thing is, it's important to point out that current is converted into light, and that light is converted into current. So it's not converted into voltage. So that comes back when I'll talk about VLC. Now, to capture more light, an intrinsic layer is put in that. So it's because it's in the intrinsic layer, actually, that the light is captured. So with photodiodes, compared to LEDs, they have a larger intrinsic zone. Now, what's the difference between a photodiode and a solar cell? Again, in principle, they are the same. It is just the way they are manufactured that is different. With a photodiode, the response time is of importance because we want to use it as a communication device. Now, the thing is the depletion zone we have. I mean, the depletion zone, as I mentioned, if it is not P or N material, it does not conduct. So you have there a non-conductor, an insulator between two conducting plates. You create a capacitance. And the capacitance, if you have a capacitance, well, your bandwidth is down the drain. So we like to keep that junction as small as possible. So to reduce that even further, a negative bias might be put on it. So we can even extract the electrons faster. Now with a solar cell, the response time is of no importance. There we want to get as much current as possible, actually. So we want to make there the intrinsic zone as high as possible. So because the capacitance doesn't matter. Also, we generate electricity, so we're not going to use that electricity to get more electrons out. It doesn't make any sense. So there is no negative bias there. And it's what a solar cell is called to be in photovoltaic mode, whether a photodiode is called to be in photocurrent mode. Now, the thing is, the wavelength, so the frequency, which means the color of the light, depends on the semiconductor compound. That's actually a field of physics. So the physicists experiment with what gives the best color at the best conversion rate. Now, the thing is also, I mentioned that forward voltage actually. That forward voltage is also proportional to the frequency. So the higher the frequency, the shorter the wavelength, the higher that forward voltage is. Now you see here, infrared, of course, has the lowest frequency, highest wavelength, and then blue and ultraviolet has the highest frequency. Now you see there a W mentioned there. I mean, white light is not a single color, but it's put on there that actually white light is produced from blue light. I will explain shortly why that is. So now what we use in LED lighting are high brightness LEDs. Now the divide between what is high brightness and what is not, there is a discussion. Most seem to agree on 50 lumens per watt. I actually have an easier definition on it. If you can look at it, it's not high brightness. If you can't look at it, it's high brightness. It's actually as simple as that. Now the thing is, to create white light, you need red, green, and blue. The reason is that the eye in the retina has actually 3 of these cones actually, so that it's basically why TV has red, green, and blue. It's because the eye detects it like that. Now the thing is, red and green lights have been around since the 1970s. Blue light has only been around since the late 1990s. So it was waiting for blue light actually to make white light. Now the thing is, green light is only about 30% efficient. Red light 60%, but blue light is 80% efficient. Now that's actually the reason why only blue light is used. As I mentioned, if you combine blue, red, and green light, you create white light. But the thing is, if you put a yellow phosphor, and the reason is that green and red form yellow, if you put a yellow phosphor in front of it, you convert it into yellow light, and if you combine that yellow light with blue light, you get your white light, and it's 80% efficient. The phosphor is going to take a little bit of that efficiency, but it is much less than what you have with the poor efficiency of red and green light. Now the thing is, there it is actually, blue light has the highest frequency, so you can down convert that. Like with red light, you could not produce blue light. With green light, you could not produce red and blue light. So it was really waiting until the blue LED came out that gave us white light. I mean, it was a stroke of luck, actually, that blue light was so much efficient, actually. That also explained why some years ago, the Nobel Prize for Physics was awarded to the invention of the blue light. So the thing is, I mean, to create either cool white or warm white is actually by means of the blue component. You see that when you create blue white light, cold white light, there is a higher blue component than in warm white light. Now, if you have colored high brightness LEDs, these are formed actually by an UV light, and they put a colored phosphor in front of that. So for architectural lighting, they use that technique. There are still RGB high brightness LEDs, but they are used in displays and TVs. The reason is you cannot change the phosphor actually, but you can change the light that is emitted by the red, green, and blue lights. Now, when we talk about LED drivers, so the ballasts, as I mentioned, current is converted into light. So those drivers are actually current sources. So, and then important with VLC, with communication system, that conversion up to saturation is linear. And that's what we want if we want to modulate signals, actually, that it is linear, that we don't have any distortion. The requirements for such ballasts is that they are power effective. Of course, you don't want to lose a lot of energy in the ballast. And also they need to isolate the LEDs from the 220 volts so that when you touch your lamp, you don't touch the 220 volts. Now, there is only one driver that fulfills both components, and that is the flyback driver. I'm not going into any details because it's way too technical, but anyone who's interested in it, write flyback drivers for LED, and a lot of information will show up, actually. Now, there are also drivers that fulfill the first requirement, but not the second, and they are used in DC spotlights. So it doesn't matter if you touch 12-volt DC, it's not going to harm you. These drivers are actually cheaper than the flyback, but you can only use them on low voltages. Now, what is the LED lighting advantage? The first thing is they are much more efficient. I mentioned blue light is 80% efficient. The best traditional lighting sources are the compact fluorescent lamps, which are only 50% effective. The TL lamps that we know are only 40% effective, and the incandescent lamps were only 3% effective. So they also have larger lifetimes. So they say 5 to 10 times longer. I mean, sources even mention they last up to 100 years. Actually, no one knows because LED lamps are only around for 20 years. So the exact, it's basically they're indestructible. You buy them and they should last a lifetime. Having said that, some LED lights break down, but it's due to a poor driver, basically, not because of the LED lights. If you got, there are actually in Thailand, there are a few dodgy local manufacturers, and I used lamps for them, and they break down after a few months. But if you got lights from well-established manufacturers like Siemens, Philips, Osram, they last a lifetime. The thing is, there is no degrading. If, for example, an LED lamp or a compact fluorescent lamp, they start degrading very quickly, actually. It is exponential, and after a year, they have already degraded by 50%. It's actually, if you change a compact fluorescent lamp or a TL lamp with exactly the same thing, you say like, oh, all of a sudden it's much brighter. And that is true. But there is no such degrading with LED lights. Something else that's important for green things, there is no hazardous material like mercury or halides. So there is also no burning hazard. I mean, you should try an LED lamp. You can touch it, actually. It's only lukewarm. Try to do that with a TL or an incandescent lamp and you burn your hands. So there is no hazard with LED lamps. So actually, you say it's more power efficient. They last longer. There is no degrading over time and no hazardous thing. So that's why it is actually a very green technology when it comes to artificial lighting. The thing is, there was a drawback. I said there was. It's no longer like 20 years ago when the first LED lamps came out, they were like 10 to 20 times more expensive than compact fluorescent lamps. Like 15 years ago, it was still 2 to 3 times, but these days, the prices are the same, actually. So that's also no longer a drawback. Now, eye safety issues. I just showed here the eye, actually, where we detect light is actually in that yellow part here. That's the retina. So that consists of actually red, green, and blue cones. And the eye is most sensitive to blue light. The reason, again, is the highest energy is blue light. So it's the highest frequency. Now, the iris actually is going to block some of the visible light. As you know, your iris closes when you look at a light source, and it opens when it's in the dark. Now, the lens, that actually filters out blue light. But the thing is, in adult people, it blocks out 65%. In young children, it's actually up to 25 years. It only blocks 20%. So that's why they say if you work with small children, it's advisable to have warm light actually in nurseries and kindergartens. It's advisable not to have cold white light, but warm white light. Yes, I mentioned that. The thing is, what I forgot to mention is that in aging eyes, actually the blue scatters a bit more. So actually it's not a good idea to have blue displays when you're in a place with elderly people, because they might experience it as a blurred vision. So yeah, as I mentioned, the thing is that there has been a study by the European Union, a commissioned study in 2017, and that actually found that there are no immediate effects with blue light. Having said that, you need to monitor it because, again, LED lights have been around for 20 years, so the real life-lasting effects we don't know. So just as a precaution matter, it's like if you work with young children, use warm light. Again, it could be in 60 years' time that they say it doesn't really matter. That is it, but it doesn't harm to be a bit cautious, actually. Now, LEDs are semiconductors, and semiconductors can be switched on very quickly. So you can actually emit zeros and ones. Now, the eye will not see it. The eye is only sensitive to the average level, so it won't see these fast changes. But a photodiode will see the changes. So you can actually use existing LED lighting infrastructure to emit communication signals. Now that concept is known as VLC. Now, as I mentioned, VLC is a form of optical wireless communication, which is a wireless connectivity via the light carrier. And the light can be any color. It can be infrared, it can be visible light of any color, or it can be ultraviolet. Now, one advantage of VLC is that the footprint can be made much smaller and much more accurate than what you can do with radio. So they're especially useful for indoor purposes, like, for example, in a museum, you send information about a certain artifact, it does not go into the neighboring artifact. A thing that we are also involved in is localization, indoor localization. So you use your LED as cells, actually, and you move from one cell to the other. An application that has gained prominence in Japan, actually, is underwater communication. Radio does not propagate in water. Ultrasound does, but ultrasound is low frequency, so you can't use it for high-speed communication. But you can use visible light as long as the water is not murky, of course, because if the water is murky, your light is not going to work either. Now, what I put here is communication between divers, but it's not only that. For oceanographic research, actually, there are, at the sea bottom, they make a communication network, and that sends signals to a boat, actually, so you can observe what's happening on the sea. Now, the thing is, as I mentioned, you can use your electrical wiring, something that is known as, well, the name escapes me a bit, actually. But you can also send signals through the electrical wiring, and then you're going to use your VLC, your LED lamps to emit a wireless signal. Now, you also want to communicate in the uplink. Now, obviously, you're not going to put high brightness sources on your computers. So there we're going to work with infrared signals. Now, infrared, you cannot send as strong signals as with visible light. But it's not a problem because the uplink is usually less speed demanding than the downlink. So then we talk about infrared wireless communication. And that's actually a concept that is known as Li-Fi. So light fidelity instead of wireless fidelity. Actually, a special form of infrared wireless communication is free space optics. And that has been around for 30 years already, actually. It's like, for example, you have a high-rise building that is serviced by a high-speed optical fiber. A second building is not. What you can do then is put a higher power laser on top of the building and transmit the signal line of sight from one building to the other. That can be at extremely high speeds, actually. Then the thing is with UV, it's actually UVA and UVB reaches us from space. UVC is blocked by the atmosphere. Now, actually, if you use UVC, so you don't have any background noise, but if you use UVC to transmit it into the atmosphere is going to work as a mirror. So it reflects the signal back to Earth. It's a very bad mirror, but a mirror nonetheless. It does not allow for high speeds, but it can allow for huge sensor networks, actually. And it's actually the American Army that does a lot of research on that. Now, as I mentioned, the antennas in VLC are the LED on the transmitter side and the photodiode, which is a large area photodiode, so it has a large intrinsic area. As I mentioned, up to saturation, the conversion from light, from current into light and from light into current is linear. So the thing is, I like to point out that we need current modulation, not voltage modulation. Again, the wavelength depends on the semiconductor compound, and I'll mention the large area photodiode converts infrared light as well as visible light. It's most sensitive for infrared light in 850 nanometers. It is less sensitive to visible light, but again, it's not a problem because you can transmit visible light at higher levels than you can do infrared light. Now, I like to point out, for those who are interested in communication, in optical fiber communication, it's 1550 nanometers. The reason is that they use avalanche photodiodes there. So they use an avalanche effect to amplify it. You cannot use that in optical wireless for the simple reason that avalanche photodiodes need a huge reversed bias voltage. By that I mean 60 volt DC. And if you have a 60 volt DC battery, it's larger than your car battery. So you're not going to carry that around, obviously. Again, the bandwidth limiting factors are the junction capacitance, both on the LED and the photodiode. The modulation format is actually intensity modulation, which is the same as amplitude modulation, except that we only have a positive signal. We don't have a negative signal. And then direct detection means a direct conversion from light into current. Yes, I mentioned this. Here you see the graph actually that shows that a photodiode is most sensitive to 850 nanometers and slightly less sensitive to visible light. Now, what are the merits of VLC? The first thing, and by foremost, the most important one, is bandwidth. Light in the spectrum, in the electromagnetic spectrum, is above radio waves and microwaves. So it can accommodate much higher speeds, up to 1,000 times more. You also know that if you want to operate a mobile phone system, you need to buy spectrum. The spectrum in light is completely free, so anyone can use it. Look, license-free does not mean unregulated. You cannot send an infinite amount of strong light out, so there are eye safety issues that you need to take in concern. But the spectrum itself is free of charge. It does not cause or create electromagnetic interference. The thing is, I'm not going into details that now, but the design of receivers and transmitters for VLC is a lot, and I mean really a lot, easier and cheaper in components than what you have with radio. Light cannot penetrate walls, so you can say that's a disadvantage. I would say yes if you talk about outdoor communication. So you're never going to see mobile phones working on light. But an advantage of that is that it prevents security at the physical layer. So if you have a blocked room, your light signal is not going to transmit in the neighboring room. I mentioned that already. The footprint can be much more accurately designed. So for indoor localization purposes or in museums, that is an advantage. There is no fading. So you know that if you have Wi-Fi, there are two antennas. They're actually used to avoid the fading. Then the drawbacks, as I mentioned, the capacitances of both the LED and the photodiode bring down the bandwidth. So, I mean, now I get a little bit technical for those people interested in communication. So you can do equalization, either active at the transmitter or passive at the receiver. Multi-carrier transmission, that's a big field of research. It's actually, instead of sending one carrier with a huge amount, we're going to send a lot of carriers with a smaller amount of bandwidth. So then you can also extend your speed. Okay, at the receiver, you can actually, to a certain extent, isolate the capacitance from the converting resistance. Yeah, as I mentioned, it's restricted by eye safety standards, so you need a sensitive receiver. Now, having said that, we have used an photodiode from Osram, actually, and without even a lens in front of it, it gives extremely good results. So if you design your receiver neatly, and it doesn't even require a lot of expertise, actually, but you can get actually very good results. Yes, there is background noise. What does that mean? The sun produces light, so that light is also picked up by the photodiode. Now, that light is actually DC because it doesn't change. It changes gradually. So, because during the night you don't have any light signal, but it's extremely low frequency. So with a simple high frequency filter, you can filter that out, actually. Now, having said that, light is statistical in nature. So you do have a change there, but that statistical noise is a lot less than the DC noise you get. Multipath dispersion. The thing is, light bounces off walls, so it reaches the photodiode at different times. So your signal is going to spread. Again, you can counterbalance this with multi-carrier transmission. There is a high dynamic range, because if you're close to the light source, you're going to receive a strong signal. If you're further from the light source, you're going to receive a weak signal. So you need automatic gain control to equalize that out. Now, for digital signals, we actually found a simple method. You just send it into saturation and it equalizes out automatically. Okay, then I'm gonna finish with the optical wireless standards. They're recent. So there was a first one in 2018, which was for lower frequencies, actually up to 10 megabits per second. But then there was a new one last year, and that goes up to gigabits per second, actually. So if you want to have a look at that, I'm not going into any details. Okay, and with this, I conclude my talk. And I'm open for any suggestions. I like to say my email address is on there. If someone is interested in a PDF of my slides, just send me an email and I email you the slides back. Okay, thank you.
If anyone has any questions regarding the session, you may ask the questions to Sir now.
So firstly, thank you for the very insightful session. One question from my end is regarding the transceiver design.
Yes.
If you can give me some insight into the VLC transceiver design and can compare it with the millimeter wave or terahertz communication designs, whether it is a analog, digital, or a hybrid
sure.
sort of a design.
No,
Yeah.
it's actually what is used is because I mean your signal is a voltage, but you need to have a current. So you need to convert the voltage into a current on the transmitter side, and that's done by a transconductance amplifier. Look that up on the internet, transconductance amplifier with op-amp. It's a very easy circuit, actually. On the receiver side, the opposite happens. So you get a photocurrent and you need to convert that into a voltage. So there you have a trans-impedance amplifier. Again, if you put in like a light amplifier with op-amp, it's done with a simple op-amp. The circuit is relatively easy, actually. Okay.
So essentially, it's less of the signal processing blocks as compared to any other.
Oh yes,
very much.
most definitely.
Okay.
It's
Thank
as I mentioned, actually to build. I mean, it's on 220 volt lights because you have that flyback transceiver there. There you need a T-bias network actually. Again, if you put in T-bias VLC signals, it will pop. That's a bit harder to design. But actually, we're not working with 220 volt lamps for the reason that students, if they touch it, they get electrocuted. So we want to avoid that. So, but we've seen that if you want to do research and you use 12 volt spotlights with easy transceivers, you can do a lot of very nice research actually.
Thank you, sir. Thank you, sir.
Any more questions?
Thank you, Carol, for a nice, wonderful session for this. I have one question regarding this organic LEDs.
Okay.
Organic LEDs. So in
Yes.
that, like in
That-
organic LEDs, what you talk about, like the material is very easy to fabricate and other things.
I know.
But when you're talking about the like lifetime other things, very less.
Yes.
So how we can improve that? Like,
No.
or your view on this? Yeah.
I have to be absolutely honest with you. We don't have any experience with the organic LEDs actually. Now, having said that, there is a lot of research being done on organic LEDs, but very little research is going on VLC with organic LEDs. So if you want to get into a relatively new field of research, I would recommend VLC with organic LEDs actually.
Any more questions?
Okay. Thank you.
Thank you, sir, for your valuable insights on LED lighting. I believe the audience is highly benefited from your words of wisdom. Moving on with the plenary talk, we now have Professor Nitin Kumar Tripathi from Asian Institute of Technology, Thailand. Professor Tripathi, a distinguished faculty member of the School of Engineering and Technology since 2000, brings a wealth of experience to this role. He also serves as the Executive Director of the Special Degree Program. He holds a PhD and Master of Technology in Remote Sensing from the Indian Institute of Technology, Kanpur, and has a Bachelor's of Technology in Civil Engineering from the National Institute of Technology, Warangal, India. His research interests encompass geoinformatics applications in various sectors such as environment, marine, health, and agriculture. With expertise in remote sensing, GIS, GNSS, and UAV technologies, his research focuses on sustainable agriculture, environmental conservation, healthcare, and urban development. Beyond his academic contributions, Professor Tripathi has played a crucial role in establishing international academic collaborations. These collaborations include Unified Bachelor's Master's Program and dual doctoral degree programs with several universities worldwide. I now welcome him on the dais and request our VC sir to felicitate him with a token of appreciation.
It is not this side. It is that side. So I will move this paper that side. इसको इधर कर दे. I'll just do it. You have to put something. Very good afternoon, everybody. I'm very, very happy to be here in Downtown University in this international conference. I have been associated with Downtown University for long. We are having a global mobility program of the student to Asian Institute of Technology. And I hope after COVID now, we will make it much stronger. Today, I have been given an assignment to talk about what is means how the sustainable development goals can be monitored. United Nations have come out with a number of sustainable development goals. One of them is the quality of life about urban people, and a lot of rapid development, urbanization and industrialization is going on in almost every country, so as in Thailand. So here I'm going to talk about greenhouse gases and urban heat island mapping using satellite remote sensing. Due to rapid urbanization and industrialization in Thailand, around Bangkok, on the eastern and western seaboard, and then how to monitor the sustainable development goal, which is happening over there. To monitor, main thing is to monitor the greenhouse gases. We are lucky to have the two satellites, GoSat from Japan and the Sentinel-5P satellites, which are giving the data about the global greenhouse gas mapping, that is carbon dioxide, carbon monoxide, and methane, which are the pollutant gases and which increase the heat in that region. To monitor that, we are going to use the data 2010 to 2021, like what has happened in the last 11 years, and see, and then also map urban heat island, and then find out the relationship between the greenhouse gases and urban heat island. So all the development and industrialization, they will emit these gases, not only these three gases, but much more. So in this study, we have taken these three gases as a case and then map the urban heat island also and see what are the effects. So study area is Thailand, as I told. So now here you can see this is Gulf of Thailand, and then on the west side, this is Hua Hin, Phetchaburi, etc. And this side is Chonburi, Pattaya, Rayong. So what is happening around Bangkok coastal, and then on these two, we will see. But since it is a freely available global data, so it can map all over the region. So, but we will particularly notice the changes around here. And this is the industrial estates that have clustered in the central and eastern side. So a lot of industrial estates have started in these areas and little bit upper north. So these are the industrial zones of Thailand. On the western side, there are very little industrial zones. Mostly they are located here. So these yellow dots are the big industrial zones, because there is a lot of development of Eastern Economic Corridor from Bangkok till Chanthaburi. So we have to get ready to find out tools of remote sensing, how to monitor the changes that they are causing. So Eastern Economic Corridor is it is going to have lot of development in the region, and then it will be like an innovation zone and everything. So we have to get ready to find out if so much development occurs, whether people will have good air or greenhouse gases will be under control or not, how to monitor that thing. So satellite data can be very effective tool. So we have got all these data from, say, GISDA, then GoSat, Sentinel-P, Google Earth Engine was used to analyze them. Then MODIS data was used for urban heat island mapping. These are methodology. I will just skip these methodologies. Greenhouse gas concentration and results. This is about the first objective, how to get the data from the satellite, then do coding in Google Earth Engine, and then map carbon dioxide using Sentinel data. Then GoSat will give carbon dioxide, and as Sentinel will give carbon monoxide, GoSat will give carbon dioxide and methane. And then we will just create the maps for number of years. And then Thailand Greenhouse Gas Management Organization, TGO, it is a public organization. They are very much worried about that, and they take data from sampling from various spots, and then they do interpolation and create the map. So we can take that data and we can find out our accuracy of the results, and then find out our reliability of our models. This is the data that has been done for 2010 to 2021 for every month. So we are choosing the similar months and then see what is happening in every month. So this is about carbon dioxide gas concentration in the Thailand and up to the ocean. So these data is very detailed, and we can just see every region what is happening over there, carbon dioxide. And then in the northeast, maybe sometimes we can have, like in May and etc., a lot of crop burning, and then see the carbon dioxide concentration over here. So we can find out and have a check. And same thing, time series of carbon dioxide in 2021, but we have records for all the years in between 2010 to 21. And then we can compare similar results, but in July here it is more, in 2010 here it is less. So this is a very good tool, very good data that can give lot of insight what is happening about these gases in that region. And then we can analyze like January 2011, 10, 11, 12, and this is very cyclic in nature. And very interesting that in similar months, the carbon dioxide concentration is rising, then it goes down. So there is a cyclic nature, like a sine curve, and then again, we see the rising trend. It means carbon dioxide concentration is rising. So it shows with the development within 10 years itself, what is the situation and what will happen after 30 years. If some policies are not done, then will it be worth living there, or it will create some problem. So this is a very good tool to monitor our SDG. And I will not go in detail about methodology, sir, but we can see the use and the value of these data. This is the methane concentration map for 2010, all the month, January to December, and 2021, January to December. And we can see a lot of like paddy is grown. So methane is generally coming from the agriculture fields. And then how lot of methane is accumulated and what is happening over there. So methane is also can be converted into some other useful things. So if so much availability of methane is there, maybe we can come out with some project to use it, to capture it and then use it for energy and other things. But right now, you can see situation was worst in 2010, but now slowly government policies are there which are controlling it. And so people are a little bit conscious about it. But on the whole, there is also seems to be rise as the activities are increasing. There seems to be rise in the methane concentration, and it is peaking like 1.9. Earlier it was in 2010 1.75 ppm, now 1.93. So not much, but it is slowly rising. This is carbon monoxide concentration map. So these three gases, you can see very good data for all the 11 years have been done, and we have seen this. Now we have the data about the whole region. Now we will focus more on the eastern, western seaboard and eastern economic corridor. So this is the average concentration of methane in Thailand, and we can see sometimes which month it is peaking, and like just after February, March it is peaking, and then it goes down. Correlation of urban heat island and greenhouse gases. Urban heat island is mapped using land surface temperature data from MODIS, and this is very useful because with the industrial activities, lot of temperature rises there, and then it stays there in that area, and it makes with the surrounding like an island of heat. And that will be, if the people are living in that, they may not have the good quality of life compared to that they are living near the forest or near the ocean somewhere where heat or urbanization or development is not that much. So you can also feel the changes in that. So now we can see here how urban heat island can be created using UHI, can be created by LST from MODIS, and then we can make a raster map and then compare it with the greenhouse gases. So this is the correlation coefficient that we found with the greenhouse gases. This is the Eastern Economic Corridor from Bangkok until here, and you can see it goes up to here, then passes. So now red color means these are the urban heat island that we have calculated from the temperature. So these areas are already very hot near the Bangkok, Chonburi, etc., and very concentrated urban environment. Then you go towards Pattaya side, and little bit in 2019 it is a little bit less. In February, January, it is little bit less. January, you can see urban heat island. February, then November and December. In many months, this MODIS temperature data is not available due to the cloud. But whatever month we could get, that we have plotted it here. And we can zoom it, and then for every place, we can see the heat islands. Where the red color is, that is heat island, then yellow and orange colors. So we can find out a complete check about heat islands. And now you can see in 2021, further down here, things are much more increasing. So temperature may not seem to be rising much, but there is a trend, little bit rise in the temperature. So it is not very alarming. I'll say it is not very alarming. The reason is that we have chosen a coastal environment, which during the evening hours and up to morning, it can absorb all the heat and carbon. So urban areas, etc., they become little bit relaxed. So things are not as bad. But if it is in a landlocked area, then you will see the problem. There is no forest to absorb the carbon dioxide, greenhouse gases, and then these heat islands will be permanent there. But in ocean environment, they deplete very fast. Only in the urban area near Bangkok, they are continuously having the heat island and very high temperatures. But as you move towards Pattaya side and Rayong side, you will feel much better atmosphere. But lot of industries there. Now we go in this further down and we can see the heat islands. So as the Eastern Economic Corridor and then, Western Seaboard, the heat islands you can see here. Western Seaboard is the Pattaya and Rayong side, etc. So now this road is almost ready, like 8-lane highway and both side 2 lanes. So 12 lanes are always having the high speed traffic and trucks, and then lot of industrial areas. So you can see slowly things are getting alarming here. And then we can see that we have to monitor and make some policies, grow some more trees by CSR, and then try to absorb these carbon dioxide and then methane, etc., and then lower the temperature of that region. So these are the coefficient of correlation. We found that carbon dioxide and methane have very, it is moderate to substantial, a significant coefficient of correlation, not very high at the moment. I will say that Thailand is managing very well. So this is a case study of Thailand. And I propose that this should be done for all the industrial development in India, and see what is the coefficient of correlation with the greenhouse gas and urban heat island in India, and how the temperatures rise. Right now it is a winter season, so everybody is happy, but no sooner March comes, then things will become difficult. Temperatures will start rising rapidly. And then we have to be very careful in the future. Now, once you see the concentration percentage of area in eastern region, so here, this is Bangkok area, and then eastern region, it's like a urban heat island. This is urban heat island, this is carbon dioxide, this is methane, is not that much here, but in the down part it is there, where a lot of agriculture activities are there. And then we can see carbon monoxide here. So this is the complete, and then in the western region, we can see urban heat island, methane, then carbon dioxide and carbon monoxide. So this is the thing, carbon monoxide and carbon dioxide mainly from industry, and then methane is from agriculture and urban heat island situation there. So we also created a dashboard like a story map using our software ArcGIS, and it can be developed very easily by GIS package. One is dashboard, where all the data and how the things are on, say, monthly or weekly basis, we can share for the whole country or the region that you want as a dashboard, and graphs and maps, everything can be there, and it can be seen on tablets or on your smartphones. So I will not go in detail about story map, but it can be easily created so that policymaker and all the people are aware what is happening in that region. So finally, I conclude that carbon dioxide, methane, and carbon monoxide concentrations are mainly in the central, northeastern, and northern parts. They are showing very high carbon dioxide concentration during summer. Meanwhile, methane and carbon monoxide during the dry winter and summer. Carbon dioxide, methane, and carbon monoxide have been influenced by urban heat island in the eastern region, by contrast of the western region. So in eastern region, we see because of these gases, UHI remains there, but in western, where Hua Hin, etc. is there, on the seaboard, very less. But if you go away from the seaboard, there are like heat island, etc. Because there are mountains in Hua Hin, and then other side of the mountain, not towards the coast, it is much hotter than near the coast. Conclusion, all three gases show similar distribution with urban heat island, forest and plantation area. So by visual, we can see that there is a good correlation, but concentration level may be different in different areas. But it is showing that wherever UHI is there, then urban, like carbon dioxide and carbon monoxides are there. And then forest and plantation area influences the reduction of the concentration of gases as well as ocean atmosphere exchange. On the other hand, the result of western region of Thailand showed both positive and negative relationship between urban heat island and greenhouse gases. So we can say that UHI is a significant tool to monitor the heat that will remain in that area. And we should not be worried just now what is happening, but seeing the past, we can project it to the future, like next 30 years, what is going to happen. If we are not careful in planning and making policies, then the life will be very, very difficult for the future generations. So this is very important that we must at least make some policies for the eastern seaboard, where the Eastern Economic Corridor is very rapidly developing in Thailand. Future recommendation, it will facilitate data is free, and all the greenhouse gas mapping data can be created in form of maps, etc., and it can be shared. We should develop a model for use in the assessment and development of the National Greenhouse Gas Report. Government agencies should have a place to store and access information easily for the policymakers and decision makers. With this, I conclude my talk. Thank you very much.
Thank you, sir, for the valuable insight. If anyone has any questions regarding the session, you may ask.
Yes, thank you very much for your presentation. Oh, excuse me. I just had a question like, how do you actually obtain the data? So what kind of sensors are used and how do you get access to the imaging?
Yeah, these data are satellite data. So GoSat Japan, they are giving the greenhouse gas data, and also Sentinel. So directly we can download that data. So it is available by the website and we can download. And then for urban heat island, Moody's is giving the thermal data in 2 bands that we have taken, and we can do it. So
Okay, thank you.
Thank you.
You know, in India, you know it better. During December, start your residue burning, rice residue burning in Punjab and all. Like, so that's a sudden rise in heat, carbon dioxide and monoxides and heat. Now, the question is, all this data, how do we make a practical application? Like, even if you look at this campus and main city center, the temperature 2-3 degree difference. Of course, there is effect of, like, we don't have carbon dioxide that much activity. The Brahmaputra is giving us cool breeze. But in these heat islands, this data shows, but how to get relief of it? Like, what kind of a strategy can be done to localized way get these gases and all? Some kind of thought on that.
Yeah. So heat island will go down only when you reduce the temperature, land surface temperature. So constructed area will have lot of heat in that area. If it is all concretized, it will have lot of heat. We should have permeable surfaces where the vegetation can be grown, and then open surfaces should not be there, like rocky area should not be there. They should be all covered with some trees or something greenery, so they can also absorb the greenhouse gases. Once we are able to control the greenhouse gases, ultimately temperature will be coming 2 to 3 degrees down. I have seen that urban area in Bangkok is around 12 degrees higher than the forest area in Khao Yai. Now you can imagine the quality of life. When 12 degrees high temperature I live, I need air conditioning and all. But in Khao Yai, there is a hilly area which is very cold. And in the evening, you really have a nice weather. But that is not there in Bangkok that time. So I think maximum up to 12 degrees I have seen rise in the urban area heat islands. And then it is very, very bad for the human health. So I think we should have policy that whatever land which cannot be used for agriculture and slopey land, etc., we should have trees, plantations, and then we can reduce these gases. Plus, wetland we should preserve. Like we have the Deepore Wheel wetland here. This must be preserved. It is absorbing lot of carbon in that one. And all the water hyacinth and all the aquatic vegetation must be there. It is very important for the ecology. I think we must have the policies, and every education institutions, I will say water harvesting is must. Then solar panels are must. We in AIT, we are going towards net zero carbon. So 2-3 buildings we have through industry support, we are converting them complete solar energy and then use less energy from the electricity department. So we can calculate how much reduction in carbon we are going to achieve. And also we are very good in water management. So all the used water is recycled for the making the area green. There is no dust. So PM 2.5, PM 10 problem is also minimized. So I think we must worry about the environment. I think now a lot of tools from the satellite data are available and we can use it for making the policies.
For the students. The other day in BBC News, just accidentally when I opened my TV, what is said, an individual in his lifetime, the amount of carbon dioxide he gives out. Now imagine 750 crores people of this world, the amount of carbon dioxide it releases, we tend to ignore. Now this can be nullified by planting 14 trees by individual in his lifetime. Means the students, if you plant 14 trees, like you won't plant 3 seeds, when it grow up, full canopy, then these 14 trees will absorb all the carbon dioxide that you release from your birth to death. So that was a beautiful, like, I think even in the city areas where the green heat areas, if we have provision of planting, that is one way. I think I found it very, very interesting news item in BBC. Thank you. I just wanted to share that. Thank you very much.
Thank you. Very good suggestion. Very nice insight. Thank you.
Sir, if I may, one last question I can ask.
Yeah.
Is there a possibility that by painting the surface with pigments that are reflecting the sun rays and not allowing it to absorb right away into the material, that will allow to reduce the urban heat island effect?
Yeah, some effect will be there, but not much, because greenhouse gases will not allow it to go away from the upper our atmosphere. It will still remain there. So from the surface it can be, but it will involve a lot of expenditure. But the solution that Professor Talukdar ji is telling about planting the trees, best one. Then preserving the water depressed areas, making the green water bodies, making the walkway and trees around it. That is the best solution for making good ecology. I think that is the cheapest and best solution. But what you are telling is a engineering solution. It will reflect the light, and we have to make insulated walls, etc., so that inside temperatures are preserved, not very hot. But that is too much expensive. It can be done. But I think if we see a city like Guwahati, etc., it may be expensive. So trees and water bodies preservation is the main thing. We must make the policies in that. Thank you. Thank you very much.
Thank you very much, Professor, for the valuable insight. Now, moving on with the session, we have plenary talk 3. For the third plenary talk, we have with us Dr. Manas Das. Dr. Manas Das received PhD in Mechanical Engineering with specialization in Manufacturing Science from Indian Institute of Technology, Kanpur, India in 2011, and MTech in Mechanical Engineering with specialization in Manufacturing Science from Indian Institute of Technology, Kanpur, India in 2004. Dr. Das' current research interests are triobiology and manufacturing. He was awarded 2012 A.M. Strickland Prize by Manufacturing Industries Division of the Institution of Mechanical Engineers for paper computational fluid dynamics simulation and experiential investigations into the magnetic field assisted nanofinishing process by Manas Das, V.K. Jain, P.S. Ghoshdassar, published in the Journal of Engineering Manufacture, Proceeding of the Institute of Mechanical Engineers, Part B. Without further delay, I welcome him on the dais and request respected Vice Chancellor Sir to felicitate him with token of appreciation.
So good afternoon to all of you. So first time I came to this Assam Downtown University. So it is a very nice campus and it is very near to the mighty river Brahmaputra. So I came from just opposite side of this river Brahmaputra, IIT Guwahati. Okay, so I work in the area of this machining area. So I shall talk about means we work in that actually different types of experimental setup, different equipments we develop. So few equipments we have developed and we did certain experiments on that. We shall discuss on that. So I'll be discussing about that post-processing of these additively manufactured components. Okay. So these are the different biomedical implants actually we are working on in last 4 or 5 years. So most of these works are actually is done by my PhD students who has already completed. So I'm telling those things actually. So first of all, actually, this is I shall discuss about what is the motivation here, and then we have developed one hybrid electrochemical magnetological finishing experimental setup, and we shall discuss actually this hip joint and then knee joint. Those things actually some biomedical implants we have polished. Okay, after that we shall discuss about certain biocompatibility test, corrosion test, wear test, wettability, and those things. And one experimental setup which is called actually directed energy deposition additive manufacturing that we have developed in our lab. So from there actually we have made certain components. Okay, so that how we have developed that actually DED, directed energy deposition, that equipment. So that also I shall discuss. So I shall so as there is a very less time is available, so I shall quickly go through their actually development phases and research area little bit I shall touch. So these are the different actually biomedical components. You know that actually this teeth. So here this the hip joint is there, and there are actually these knee joints, and there are different actually bone plates are there actually. If this femur these bones are actually broken, so we use actually these kind of bone plates are there. Okay, so this is the hip joint actually. Here the spherical parts is there. Okay, so if it is broken, then it is actually it is actually replaced by this kind of hip joint where the spherical components is there. And after that actually there will be acetubular cup, which a polymeric base actually acetubular cup, and this is actually made of titanium alloy, cobalt chromium alloy. So there are different kinds of alloying elements are there which are actually biocompatible components, metals are there. Okay, so what we did actually, we thought of actually, because most of these components those are actually imported from outside, so it is not compatible to our people from India. So that's why actually what we did, we have actually developed this fabricated this kind of components using additive manufacturing process. So you know that actually in additive manufacturing there is a layer by layer deposition of these metals, and then any kind of complicated components actually we can develop. Okay, so these are the actually different features of this additive manufacturing components. So individualization, so any kind of complex shape, any customized components actually biomedical implants can be developed, any kind of complex shapes, and there are functional integrations are there. Okay, so one component can work as a entire, so it is a combination of 2-3 components, so there is no joint actually required. Okay, so first we have developed this kind of components actually using fabricated using DAD process, and after that you know that in additive manufacturing there is a loose powder particles are there, so there is a layer by layer deposition is there. So that's why actually there will be a striation effects will be there. So there are balling effects would be there, loose metal powders will be there. So there is a uneven surface actually, this uneven surface which is actually required to get polished into a nanometer level. So this surface actually over that actually one acetubular cup will be there, and there is a continuous relative motion in between these two components. So that's why unless there is actually this surface is polished into the nanometer level, so there will be lots of wear and tear will be there. So in the next slide you see that actually, so this is the hip implant here, and before over that actually this kind of acetubular cup will be there. So now if there is a debris particles are generated, so here these debris particles, if it is generated, then it further actually it creates lots of wear and tear on this surface, and then the person or patient who is actually wearing this kind of components, so he faces lots of actually pain. Okay, so over time actually this debris particles actually it mixed with the body fluid, and then our body actually thinks of actually this foreign particles, so there will be lots of cytokines release will be there, and then after that actually whatever this there will be osteoclast will be there. So whatever this these cytokines, because of this generation of that, actually it reacts with our own body parts. Whatever this implant is there, hip implant, and then there will be further wear and tear, and there will be loosening of this hip implant, which is actually inserted in our already available bone. Okay. So also there will be a systematic toxicity on these kind of components. Whatever this debris particles are there, it affects our kidney, heart, brain. Okay, so these components are actually affected. So that's why our requirement is that actually whatever this surface which is in contact, there is a relative motion with another component. Okay, so this kind of components has to be actually surface finish should be in the nanometer level, so that there should not be any further wear and tear will not be there. Okay, to avoid that. Okay, so that's why we have developed one experimental setup which is called electrochemical. So it is a combination of two processes: electrochemical machining and magnetobiological finishing. Okay, so this MR fluid, you know that actually. Okay, so it is not coming. So you can see here, these are the MR fluid here. So when you apply certain magnetic field, what happens actually, these iron particles inside that MR fluid, it becomes actually this kind of chain kinds of structures will be generated. So here you can see, okay. And then if you mix certain kind of abrasive particles into that, these abrasive particles, okay, so mixed with these iron particles. So these iron particles will abrade, or it will include this actually, these abrasive particles give strength to these abrasive particles. And now, so it works as like a polishing brush. Now on a surface, so it can take the shape of the workpiece. Any kind of complex surface you can polish by this kind of smart magnetobiological polishing fluid. But this MR fluid actually, it works on a surface where actually surface finish is less. Okay, so less than 1 micron. So that's why actually we have added this electrochemical machining. Okay, so in electrochemical machining, what we did actually, this magnesium chloride and ethylene glycol as an electrolyte we have used. So ECM, you know that actually it is an anodic dissolution process, where so it is governed by this Faraday's law. So this kind of chemical reactions actually occurs. And then, so this workpiece material, it is actually a titanium alloy of grade 5. Okay, so this initial oxide layers actually, it is very less, it is not uniform also. So after electrochemical machining, you can see that actually there is a thick layer, around 75 micron thick layer of this oxide layer, titanium oxide layer, which is generated. So it is generated because of these chemical reactions with the electrolyte on the titanium alloy. Okay, so now for magnetobiological finishing process, we have this electromagnet. Okay, so this core material, it is a pure iron, and this is the coil here actually we are using. So here we have actually developed through simulation this kind of actually electromagnet we have developed. Over there actually we have used actually mu metal for shielding purpose, actually magnetic shielding, and just below that actually we have placed our this MR fluid. Now we have to move this actually this tool over the surface, and at the same time as this we have used ethylene glycol and magnesium chloride as a electrolyte. ECM process and magnetobiological finishing process, both the things will work. So we have a 5-axis CNC machine, you know, all of you. CNC machine XYZ movement is there, and there is a rotational motion, and also there is a and B, two rotational motion is there. So this is the tool here actually what we are using, and so you can see that excited view of this tool here, and it will move over the surface, and any kind of complex surface can be polished by this process. So after that actually we have done certain parametric study. Okay, so by changing current, then percentage of electrolyte, finishing time, and rotational speed, and we got that actually optimum parameters. Okay, so before finishing, you can see that pencil, it is not reflected. After that actually you can get this actually reflected surface. After that we have compared with that only magnetobiological finishing and hybrid. With the hybrid process, we have found that with hybrid process actually we got finishing within 30 minutes. But in case of only if you are using magnetobiological finishing, it takes actually lots of time, 3 to 4 hours. So after that actually we did that XPS study. You can see that actually around 75 micron this oxide layer is actually generated. So this oxide layer, it will help to further removal of this actually this kind of, because it is a very hard material. Okay, so further, so this whatever the cytokines storm is there, you know, so that it will not affect on the surface on the bone material. So this kind of so after that actually, so you can see this is the hip implant here, spherical parts. So what we did actually, first we have done because it's surface finish which is developed by this additive manufacturing process by layer deposition. Okay. So after that, actually, what we did certain chemical reactions, chemical etching we have done. Okay. So after chemical etching, its surface finish, it is reduced to less than 1 micron. And after that, actually, we did hybrid electrochemical magnetogeological finishing and this kind of mirror finish surface we receive. So these are the different defects are there when you are using any components, fabricating any components using additive manufacturing process. This kind of balling effects will be there, loose metal powders will be there. Okay, so these things actually has to be removed by our finishing process. So chemical etching, actually we have used hydrogen fluoride and nitric acid. Okay, our workpiece actually did inside that actually this chemical for a certain amount of time, and we have found that actually this, because of this chemical etching, its surface finish actually tremendously reduced from 11 to 12 micron to less than 1 micron. Okay, so after that actually we did after chemical etching. So before chemical etching, so after this the chemical etching, so initial surface, and this the this the after etching this one. Okay, so FM picture also we have taken here. So surface finish, it is tremendously reduced. So around it is 14 to 15 micron. So here it is 0.9 micron. So after that, actually we did that polishing action. So this hip implant and this is the tool here. Okay, so this in the next video you will see that. So videos are not running. Okay, so here this machine is actually 5-axis machine we have used for polishing purpose. Okay, so here this you can see this is the after etching, and then after polishing you can get actually this kind of mirror finish surface. So here this whatever written on the work paper, so it is reflected on the surface of the workpiece. Okay, so this is the final surface which is red color, and this is the after etching, chemical etching, which is surface. Okay, so you can see tremendously actually it is reduced. And after that we have seen that actually from thermal camera we have seen whether any shape change is there or not. So after that we have done certain biocompatibility test. Okay, so we have surface roughness we have measured, and after that actually we have measured skewness and courtesies also. So skewness, courtesies, this kind of spike formation you can see that actually. Okay, so if there is this kind of spike formation is there actually, so in that case our more wear out will be there. And this kind of actually whether this more peaks are there or more valleys are there, so these things actually we can check using this skewness curve. Okay, so after that actually this Abbott Firestone curve also we have seen. So this is the initial surface. So after that actually this chemical etching, and then after polishing actually using magnetogeological finishing, we have seen that actually what kind of things. And after that we have done this actually corrosion test and wear test also. Okay, so after that we have done this wettability test. Okay, whether it is hydrophobic or hydrophilic surface is there. So after that what we did actually, if suppose we are going to polish this kind of actually these bone plates. So bone plates, lots of holes are there actually. So these holes are actually polished by this magnetogeological finishing, hybrid electrochemical magnetogeological finishing process. As our MR fluid actually it contains lots of actually these iron particles, so it stays over the surface. So that's why what we did actually we filled up with that wax. And after that we polished using this our tool, so this Nobel polishing tool, and we found that actually this after polishing, so it is polished properly. So so that actually that the syringe actually metallic syringe we have used, which is filled up with wax. So that is a coil which is heated. So certain amount of wax actually it is deposited over there. And after that actually we have used polishing. Okay, so you can see here actually this before polishing. So this element which is actually developed by additive manufacturing process, which is SLM process, selective laser melting, and then after polishing you can see this kind of reflective surface we got. So similarly on these bone plates also we have done similar kind of analysis also we have done. So this is the bone plate. So this is the bone plates here, and after that we have done on the internal surface of this acetobular cup, which is over the hip joint, which is kept over there. Okay. Okay, so certain case studies we have done. Okay, so after that actually I am going to explain how we have developed this actually DED process. So in DED process, actually here this gravity-based deposition, powder deposition system we have developed. So this kind of gravity-based system, which is actually required in case of when we are using actually this electron beam type power source. Okay, so in that case, actually you have to have a channel, okay, container. So machine chamber, which is actually this. So which should be actually vacuum chamber is required. So in that case, actually this kind of normal kind of actually power delivery system, but assisting gas is required are not used. So you are using actually gravity-based system. Okay, so here actually there is a screw conveyor. Through this screw conveyor, actually these particles are actually flowing over there, and then there is a pressure is there actually. So this kind of marks actually starting groups actually have generated on this nozzle when it rotates. So these powder particles actually it comes through this slot and it will. So this is the focal point here you can see, and at the center actually there will be a one IPG. So laser source will be there. Okay. So we have simulated this one using a DMM software, and this is the final nozzle actually whatever we have developed. It is attached to actually the CXC CNC machine here. You can see on the right hand side you can see. So that is a CNC machine, and here we have actually 4 axis also there, so we can rotate the workpiece also. Okay. So here so this video is not coming, so you can see here actually through this nozzle at the center this IPG laser. So it is a diode laser we have used, and on the workpiece here actually it is deposited on the workpiece. So any kind of repair or maintenance work can be done by this kind of process. So here actually I am showing little bit how we have actually developed another process actually. So here this is the femoral component, this is the polyethylene component is there. Okay. So knee implant, basically this kind of knee implant, which is actually what old age. So we need to replace this kind of knee implant. So here actually this knee implant, which is manufactured by a 5-axis CNC machine. After that actually we have polished here. Okay. So for that actually we have developed this kind of tool here, where this is the magnetic field lines. You can see this kind of tool we have developed. Okay, so here there is the new metal shielding material we have used. At the center actually we have kept our this core material. Here actually these permanent magnets, NDFE based permanent magnets we have used. Okay, so it is attached to actually this vertical axis of a CNC machine, 3-axis CNC machine. So here we have attached this workpiece here, and then through using this tool actually we can polish over the surface, entire surface of, and every time actually it is perpendicular. So this tool is perpendicular to the workpiece surface. Okay, so after finishing you can get so this kind of mirror finish surface, and after that we have measured this. These are the different measurements. So the surface roughness parameters actually we have done. So this is also one setup actually for which is called actually rotational magnetorheological finishing process, which have developed in our work. So this kind of reciprocating motion of this MR fluid is there. Through this fluid also moves, and internal surface actually it is polished. So this is the actually electromagnet or permanent magnet, any kind of magnet actually you can keep it here. Okay, so this is the finishing region. You can this kind of small miniature gears or any kind of complex shapes actually you can polish by using this process. Okay, so you can see here actually how this MR fluid is passing through that. So here actually this miniature gear we kept, and it is coming outside from the workpiece. Okay, so whatever this marks actually which is there, actually it is polished properly after that finishing. You can see that whatever these bars which is generated by YDDM process, it is removed, completely removed by this process. Okay, so these are the different setups in our lab. So this is already magnetorheological finishing. So one actually plasma polishing process, we have a tie-up with ISRO Trivandrum. So they have given these kind of components. So we have developed this setup here. So this setup also rotational MRF process I have shown. So this is another MRF setup, and one micro ECM setup, one actually micro ADM setup also we have developed in our lab at IIT Guwahati in mechanical department. Okay, so conclusions I am not going through again. Okay, so thank you.
Does anybody have any questions? Sir.
Yes, thank you for your presentation. I was just wondering, do you also collaborate with medical faculty on this?
So I collaborated in our GMCH, one Guwahati Medical College in our North Guwahati, it is there. So whatever this actually knee implant, hip implants, actually there, those things we have. And then actually our functioning related some materials also we have developed. Okay, so where the density like in our bone, so this density actually changes. So that also we have collaborated there.
Okay, so they evaluate the progress of this as well. Are they involved in the evaluation process?
So evaluation actually this through actually patient evaluation we have not done. So still actually we are now in developing stage. So first we want to get that actually this required criteria. So that's why actually biocompatibility test, and then we are test erosion corrosion test. Those tests actually we are doing. Okay, how it will work in our body fluid. So those tests actually we have done. So now we are actually collaborating. We have started working on that, whether it can be implemented on a patient or not, that we are checking now.
Okay, thank you.
Any more questions from the audience?
Okay.
Seeing none. Sorry.
Thank you.
Thank you, sir, for your really insightful words. Now, after this, we will have lunch. All VIPs and keynote speakers will have lunch in boardroom first floor C block. The program, that is technical session 1, will resume again after lunch from 2:15 onwards. Please head towards the room for lunch.
Also, I request all the paper presenters as well to please come back to the venue from 2:15, because after that we'll be starting with our technical sessions, and we will be having a group photograph as well with all the dignitaries, co-chairpersons and the chairpersons as well. So to all the participants as well, please have your lunch, and we are expecting you in the venue from 2:15. Thank you.